the tech people are watching. Anyone else know if other people are watching them? I'm watching. You're watching the videos? Oh.
And how are the,
Okay, so last time we finished by talking about these spun two-knots. Did anybody have any questions about that? Was there anything I needed to revisit? If not, I think I promised this time we would discuss spun torus knots, a knotted tora formed by spinning. Okay, so if you remember, the way we formed the spun two knots was we punctured a knot in S3 at a point on the knot, and then we spun the resulting three ball through. So this time what we'll do is given a knot, we'll form a three ball one manifold pair. No, I wrote it wrong. Oh, so I'm looking at the wrong page. Oh, good. Form this guy by puncturing S3 away from K. Okay. So instead of getting a knotted arc in here, we get just a knot contained in a three ball instead of a three strip. And we can do the same spinning and twist spinning operations. Okay, so as before, we can spin this pair B3K through through S4 minus the neighborhood of the unknotted two sphere, which is just B3 cross S1. And this time we get a knotted torus. Okay. And we can also call the spun, what is it called? I don't even know what it's called. The spun torus. It's called the spun torus. Spun torus knot? Yeah, spun torus knot. TOK. We can also add end twists. To get something which we might denote by, you might even call the end twist spun torus knot of K, but actually we're not going to give it that name because there's a proposition which is due to Boyle, 1993, which is that if we do n plus 2 twists of K as we go through this spinning motion, then this is the same knotted surface that we get if we do just n twists of K. Okay, so the twisting can actually be undone mod 2. Okay, so what we actually get is only 2 interesting knots. Okay, what we get is we get the spun torus knot, T of K, and we get the turned torus knot. That's what it's called in literature. T, say 1 of K. Okay, where we go around once. Okay. And yeah, so again, I could reassign you an exercise, which is that pi1 of S4 minus the spun torus not okay is isomorphic to pi1 of S4 minus the turned torus not okay, is isomorphic to the group of K.
Do you know if this Boyle's result is just a bell trick?
Sense. Yeah, in some sense it essentially is. It's just a Gluck twist.
Oh, I see.
Yeah. Bell trick. See, somehow bell trick.
You know, pi one of SO.
Oh, yeah.
I
I mean, it is that. Yeah. That's right. In one guy's right. But you know, in such a way that it isn't true for the twist spun.
Well, that's because you got fixed points. Sometimes
Exactly.
You can't move the north and south pole. I mean,
Right. Yeah, yeah. So the key thing about pi1 of SO3 is that you can choose any axis. That's right. Okay. So again, we get you know, knotted surfaces because they're non-trivial pi1. And then, so the theorems that get attached to these examples are due to Gonzalez, Acuna, and Boyle. So the first, and this says that S4, the exterior S4 minus the exterior, I want to do exterior, maybe I'll make this. The exterior of the spun torus not okay is homotopy equivalent to the exterior of the turned torus not okay. So not just pi1, but actually homotopy equivalent. And then I think this might have been Boyle's advisor. I don't know, maybe that's not true. Or maybe it's just that in his paper, he attributes part of his results to Professor. I guess that doesn't imply that it is, but anyway, at basically the same time, we have two observations, which is that these things are not diffeomorphic. They're not. I mean, they're not homomorphic. And then secondly, that why did I write it like this? The spun torus knot, or maybe I should recover it. The turned torus knot is not equal to a two knot connects some a standard torus. Now I don't know why I wrote turned torus not there. The spun torus, same is true. Where's Jason?
Do they have different peripheral subgroup or something?
That's what this result is essentially doing. He's looking at an intersection forming the boundary through torus and showing that some longitudes pair differently. But what I wanted to ask you, it is true that the spun torus is not the spun two knot connects on that torus.
That was in a paper without proof. So
Yeah,
I think
yeah, somehow somehow you do attach a tube, but it's an interesting tube that runs through the middle. So I think this is also true for spun torus. But okay, I should put that up. All right, so that's what I wanted to give in terms of motivating examples of knotted surfaces.
is that second, so I see, so neither of these facts that Boyle proved follow from pi1 because everything's right.
Yeah, or any homotopy groups, in fact. Yeah, yeah, and so like Jason said, it actually involves looking at sort of the peripheral three torus, and he comes up with a Z mod 2 value, what's essentially looking for. Okay. Any questions, any other questions with these examples? Okay, cool. So then the next thing we should talk about is, now that we are sort of convinced that there are at least interesting objects to study here, we should talk about some sort of systematic way of studying them. So the first thing we'll talk about is a classical way of thinking about surface lengths called the normal form. Okay, so this is gonna feel a lot like the lectures on bridge physics. Actually, this will feel probably more like the lectures on bridge splittings than the bridge dissections. But well, anyway, all right. So let H from S4 union S4 to R. And again, how am I thinking about this target? Thinking of the target as R union plus or minus infinity, where the restriction away from the poles maps onto R. So this should be the standard Morse function. And by standard Morse function, I mean only two critical points. Okay, so standard height function, right? We can think of S4 as negative infinity, a point negative infinity, union S3 cross R, union a point positive infinity. So we have all these concentric three spheres which shrink to a point on each end. This is the suspension that we talked about last time. Okay, and let's let S inside S4 be a surface length. And assume that the restriction H restricted to S, which maybe I'll just denote H, because H as a function on S4 is not so interesting. Maybe I'll try to be careful. Is Morse. So this is a map then from S to R. So this is an honest map from S to R because we assume that our surface length miss the poles of S4. It's contained in this product region. Okay. Is Morse. Okay, so let's, so the first thing we're going to do is talk about critical points of Morse functions on surfaces. Okay, so the critical point Z of this Morse function is either index 0, 1, or 2. Okay, and for every regular value t in R, we have that the pair, switch to H. H inverse of t, comma, H restricted to S. Where do you put the inverse of t? What is this object going to be at a regular value? Yeah, it's going to be a link. This is if amorphic S3L. Is a link. Or S3. Yeah, the empty link. Which is prime. Exercise. I'll get Dave to make it. Okay, so what do local models around these critical points look like then? So let's draw a couple of these. This is where being able to copy and paste your notes is nice. Okay, so what I'm trying to do here is take five cross-sectional pieces, five regular values. Five cross-sectional pieces. So each of these is going to be H inverse of T is a copy of the 3 sphere. Okay, so let's look at an index 0 critical point. So what we see is and we'll center, we'll do it like this. Well, this be 3 equals 0, 3 equals 1, 2, 3 equals minus 2. And we'll suppose that our critical value, our critical point C is at t equals 0. So at an index 0 critical point, what we see going down is just emptiness. And what we see going up is a cone or a disk, which we'll call a cup. This is a cup. So that's the local model around index 0 critical point. See if I can do this again. And then the local model around a, let's skip. Local model around an index 2 critical point. Where did K come from? Is just the opposite of an index 1 critical point. So it looks like this. And this is what we'll call a cap. Okay, the Dunn's cap in this case. Okay, so that's pretty good. And then the interesting one here is K equals 1, okay, corresponding to a saddle. So at time 2, we see, I always like to work down for some reason, even though it's backwards of the index. But time 2, we just see sort of 2 pieces of our surface are intersecting this cross-section in a link. So we see 2 pieces of a link, which get closer together until at time 0, they actually meet. And so at this cross-sectional piece, we have a singular object, which is almost a one manifold except for this immerse point. And then they split on the other side, but they split sort of in the orthogonal direction. So this is a saddle or a band. We'll see shortly why I call it that. Okay, so those are the local models around the critical points of restriction of the Morse function to the surface. So let's revisit each of these a little bit. So the way I want to think of the cup is, I sort of had a picture like this for the cup. And what I would actually like to do is I'd like to flatten my surface a little bit near Z. Okay, so what that means is I'm going to sort of take a very small neighborhood at this point, and I'm going to just project, I'm going to push the isotope the surface until a disk neighborhood of the critical point lies flat. So what that's essentially going to look like is something like this. So if I do this, then when I see a cross section that contains that index 0 critical point, what I'll actually see is a flat disk. That's what just appears out of nowhere. Instead of having a point appear out of nowhere as you travel up in time, just a full disk will appear. And then after that, the boundary of the disk will rise upward. Okay. And then similarly for the cap, we'll do the same thing. This one's a little easier to see because I'm actually shading the top of the cone. Going down in time at a cap, we'll just see a disk appear, and then its boundary will continue to trace downward. This is most interesting near a saddle. It's kind of an involved picture here. Okay, so this is the local picture around a saddle Z that's traced out by that moving picture there. So you see we have, and it actually matches that, which is good. So we have the two pieces which come together, get closer and closer until they split, and then they're sort of moving apart in the other direction. And the way we want to transform this is, again, to flatten the surface just in the neighborhood of Z. So it looks like the picture I have here is something like this. Something like this. So, so near Z, we get a flat square. And as we travel up in time, it's this, the front and back boundary of the square disappear, and only the sort of left and right pieces survive going up. And then going down in time is the opposite edges, which go down. And if you think about what's happening in the link picture, you know, the picture for a link is we see this, then we see this, and we see this, where what happened in between was we attached a band, and so I guess we have the yellow portion, you have to see the yellow sides of the band, where the band is attached, get replaced with the blue sides of the band, which survive going forward. And away from this band, actually, there's a better way to draw this. Sorry. Make it a little bit more political. Okay, so these sides are blue. That's what survives here. And these sides are yellow. And that's what survives here. And the white is sort of preserved on either side throughout. Okay, so the take home here is that these saddles correspond to attaching bands at a cross section of it. So this is important. Okay. All right, so let's look at some examples of moving pictures. I'll try to do a few of these carefully. So the first one, you know, so what do we see? At first, we don't see anything, and then all of a sudden, we see a disk. So I don't know how to do this. First, we don't see anything. I don't know how to draw nothing. Then all of a sudden, a disk pops into existence. As we move down from that cap, we just see the boundary of the cap, which is an unknot. And so one thing it might do as it flows down through time is it might isotope itself around in S3. Okay, as it goes down, we've got all these S3 levels. It could move sort of horizontally in S3, in these horizontal cross sections. But then eventually, one thing that might happen is, after moving around some amount, we encounter a saddle, which manifests as a band suddenly appearing in the S3 cross section. I'll redraw this. It's like when you're watching a show and after you come back for commercial, they tell you what happened last 45 seconds ago. Well, this is it. And what happens immediately after this is that the band resolves. And then we go down a little further, and something you can imagine happens is one of these guys gets capped off, and then after that we just got the big guy, and then maybe he gets smaller and caps off. Okay. And so then what we've described then is a surface which is sitting in S4 with respect to the height function, so that it has a single cap, a single band, and two cups. And of course, this gives us a cellular decomposition of the surface. So we can calculate that the Euler characteristic of this surface is going to be the number of caps minus the number of bands plus the number of cups, which is 2. And so, and it's connected, and we didn't do anything that would mess up orientations. That's sort of something to check, right? So maybe we can think about that a little bit. So if we orient, let's just look at this. If we orient the link in the cross section where the banding is being performed, which I guess is the same as this one, then what we see, then this, then the pieces below and above it, particularly below it, inherit an orientation from that. And you can ask, if they inherit an orientation, rather. And what we see in this case is that this local picture around this band can be coherently oriented. In other words, this band is preserving the orientation from one level set to the next. Okay, so what we see is that this is a two-sphere, and a more schematic kind of view of this thing would be something like this. A maxima to minima in the symbol. Okay. Let's look at a slightly more complicated example. So again, there was nothing, and then there's a disk, which becomes an unknot immediately after, which isotopes around, do something like this, which then is met by a band, which then resolves, which then unknots, caps off, and disappears. So this time, the Euler characteristic is going to be 1 minus 1 plus 1 is 1. Okay. And if we think about orientations, we can orient the cross section where the band lives, like this, and that will agree above here because it's the same piece of the surface. Nothing has changed. But then when we push these orientations down, this just becomes a piece of this sheet on the back, and similar, this becomes a piece of this sheet, and on the right, this sort of becomes, this is still this is still this, and what we see is that the orientations on the surface no longer agree. So I guess I can say the words. That this is called a coherent. I wasn't planning on saying this. This is a coherent band, and this is an incoherent band. Those are some words you might see attached to this sort of behavior where the band is causing an orientation reversal. And what that means is that an irregular neighborhood of this band, what we're really seeing is a Mobius band of some sort. And in particular, the capped off surface is going to be, so this is the standard cross cap P plus in this case, and this was the unknotted two-sphere view.
you kind of cheated with the P plus because you didn't, it's not a real crossing. You really twisted the band is what you did when you attached it. Is that right?
Well, I actually worked kind of hard to make my band look not twisted.
Right.
But bands are bands.
Right.
This, this thing is living in S3 and is only being considered up to ambient isotopy. So you're saying maybe I should.
Not that you should.
I don't think I cheated. Did I? Well,
I don't know.
You could draw without the crossing.
Yeah,
you could draw without the crossing with the crossing in the band.
right. So it's not really the non. I don't know.
No, I want to understand.
I don't have anything.
Okay.
to say.
I retract my interest. Okay. I think that's it. That does look like what I drew for the positive cross, the positive uncounted RV2 P plus. I think so. Assuming all the orientations have been done correctly. Okay, let's do another example. All right, so in this example, the first thing that's going to happen is we're going to sort of right off the bat have two caps pop into it. So, in general, we're not really assuming anything about isolated critical points unless we want them to be isolated, and then we assume they're isolated. But these two happen at the same time. And what happens after they're born and they move down a little bit is they start intertwining like this. Might be useful actually to color them. Okay, so this is a two-component unlink, as you can probably believe. I'm gonna have to redraw it a couple times. Oops. Okay, and then in this time slice, we're going to have a band appear. And then so immediately after that, let's see what we have. This will be a little different. We see this cross section. And then I'll try it the same way. And as we go a little bit farther down, we have another band, and it's chosen so that it's basically just undoing what we already had done. Get this, they unravel, and they die. Okay, so this is a little bit more exciting. So what's cool about this example is it shows, these pictures. I mean, the first picture I did could essentially have been done in three-dimensional space. I mean, could have been done in three-dimensional space. This one couldn't be, but it almost could. But it at least shows a little bit how having the ambient free space in each cross section lets you do some interesting things. But this one really shows you sort of the full picture of what's going on, which is that these cross sections really can be linked and knotted in interesting ways. So, so what we get here in this case is the oil other characteristic is 2 minus 2 plus 2. It's 2 again. And again, you can check that it's connected and oriented and whatnot. And then so the claim in this case is that S is the spin of the trefoil T32. In particular, pi 1 of S4 minus, well, yeah. The claim is that this is the spin. I didn't think about whether that should be an exercise or not. Yeah, I think this is actually approachable as an exercise. And the way to think about it is we want to spin the trefoil when it's in a particularly nice form, namely, we want to do something like this. That's different. That's what I want to do. Okay, so what I want to do is I want to put the punctured trefoil in the 3-ball so that it has 2 minima and 1 maxima. And when I spin this object through 4 space, hold on, I'll do it like this. I want to think about the types of critical points that these 3-dimensional critical points will sweep out. So what the spin is essentially doing in this schematic is, here we are we have S3, half of 3-ball and S3. And what we're essentially going to do is we're just going to let it swing down through B4, sort of being careful with the height function. You know, the height function is, this is the equator of S4, and the height function goes down, up. And so when we swing this down, we can think about what's going to happen with these critical points. They're going to contribute, well, the result will be a surface in normal form, and the 3-dimensional critical points will give rise to 4-dimensional critical points. In particular, one thing you'll see is that when you get over here, this is something I drew on the board when I was talking about spinning, but nobody asked me about, so it went unmentioned, which is, it was also confusing because I drew the figure eight. But when you push this 3-ball through and you come up over here, the union of S3 is 3-balls really comes with an orientation reversal on one of the 3-ball lines. So you're going to get the mirror one. Oh yeah, okay, good. And so if we start with T32 over here, what we're going to get over here is the mirror T32. And you can see that the points we're pivoting along provide a nice connect summary. So now all you need to think about is how these minima on K, when they go down, they don't give us critical points until they reach the bottom. They give us 2 minima, and then they come up. And this maxima will actually go down, and it's going down, but when it's at the bottom, it's a maxima, so it's actually a saddle, and it comes back up. And so what you'll be able to see is essentially this half, right? You'll see that half of the picture below, or maybe sorry, I'm just including this. Oh, I didn't do my commercial break, right? Okay. You guys know what's going on. Right, so pushing this thing down and through it's sweeping out this disk whose boundary is the square nut. One of these days we'll have a breakout session on ribbon disks. And then you also have to think about, well, now what happens above? And it should be sort of this, it should be sort of symmetric because the spinning is sort of symmetric. And that has to do with the fact that this orange band and this green band are in some sense exactly the same. Because like in this band, in this picture, if you remember where the orange band was, it was sort of right there. If you remember, and that's exactly what we did with green going down. So we sort of attached a band, then we've attached its dual. And that is representing the fact that this spun trunk was actually a double of two sort of standard ribbon discs for this square knot. This thing's called the square knot.
So normal form means this.
Not quite. Means what?
This picture.
Oh, I didn't define normal form. Oh, I see what you're asking. Oh, I kept saying normal form. I see. No, I didn't tell you normal form. So what I should have said when I was saying normal form was just like more something. I don't know. Okay, let's here's the normal form. I see. Normal form is just a statement about where the critical points are. Surface link is in normal form, which is basically like bridge position with respect to H if one, H of Z is 2 for each cap Z, 2, H of Z is 0 for each band or saddle, and 3, H of Z is -2 for each cup. In other words, the Morse function is essentially self-indexing on S. And I guess these should all be HS's. I guess it doesn't matter, but anyway, I guess it kind of is. Okay. Okay, and then 0 of Auchi, Shibuya, Suzuki. 2 is that every surface length can be put in normal form. And the isotope to be in normal with respect to okay. So in particular, all of the examples I gave, they weren't quite a normal form. The first two were because we only had one band. But this one, I guess, is not quite a normal form because the bands occurred at different heights. And I guess the most difficult part of this is essentially claiming that if you have two adjacent critical points that are both bands, then you are free to interchange their height or make them have the same height. So I think I do want to sketch a proof of this, which I was going to start off by having some conventions. But I'm wondering if I could skip the conventions and start over, since we only have like 33 minutes left. All right. Okay, maybe what I'll do is I'll tell you the conventions, and then actually then I can let you think about the proof over the weekend, because it follows more or less once we think about it. Okay, so some conventions that we'll have is for a compact submanifold, or maybe even not manifold, of S4 and interval I and R, where I'm thinking of this as either closed, open, or a point. Okay, so any compact, or no, any connected subset of R, really. Let's let X sub I denote the intersection of X with the inverse of I. In other words, the intersection of X with all of the level sets corresponding to the interval I. So in other words, S4 I is just H inverse of I. And this is diffeomorphic to S3 cross I. So that's the first convention, which is fairly standard. So the next one's a little bit different. For a compact subset Y of a level set, let's say S4T, where T's and R. Let Y, I'll write brackets Y here, or bracket I. YI denote the result of pushing Y along the gradient flow of H during time I. So for example, if L is a link in this cross section, then L T minus epsilon T plus epsilon is a cylinder. Actually, sorry, I think I misspoke here. The cylinder, the vertical cylinder. Resulting from, okay, so if we have a level set, we have some compact subset, we can think of the sort of vertical cylinder we get by flowing that thing up and down along an interval I, where I should include the level T. And notice that this may not, if L is a cross section of some surface, this may not coincide with the surface. So for example, maybe we have a cap like this or something, right? And we pick this cross section L, then the vertical cylinder we get by pushing this up and down may not actually coincide with the original surface. But what we're going to try to do to prove this theorem is essentially say, yes, we can isotope our surface until it is vertical. Yeah, that's it. Yeah. So think about that. Try to do it on your own over the weekend, and we'll see it on Monday, and we'll do something else after that. Any questions about this?
No relative force function to it. It's not like a 4 or 2 dimensional result.
Yeah, no. This probably follows from the right notion of relative Morse theory, relative surf theory. Okay, my understanding is that though is that that's not, it's like not the most well documented.
Certainly not documented. And you gotta worry about, the instructions to moving things past each other are more complicated.
A lot of people will just say, this just follows from survey theory.
But things are ambient, so you're trying to do things not by changing the function, but by changing the embedding. And that's harder in general.
Yeah, because in particular, you don't want to, like, say you want to cancel critical points of the restriction to the surface or something. You don't want to create any critical points of global Morse function. So you want to sort of always be working within Morse functions that are Morse topic to the Trisections one.